Hello and welcome back once again. So right now we are discussing about grain refinement by severe plastic deformation. So I suppose by now we understand what is meant by deformation by shear. Okay. So this we have seen with an example of this ECAP process, which has different variants also, and each of these variants will have their own mechanism of deformation. Okay, so now let us try and understand as to how this severe plastic deformation leads to grain refinement in terms of those dislocation mechanisms. So if you remember, I said for a process like this, severe plastic deformation process, dynamic recrystallization is going to play a very crucial role. Because what happens here when you subject the material to severe plastic deformation, you also generate a lot of dislocations, right? So dislocations in such a high number will definitely going to play a role in the process of grain refinement in this particular case, okay? Depending on the conditions, the deformation conditions and the material properties, the type of dynamic recrystallization can vary from material to material. Okay, we have already learned about different types of dynamic recrystallization, and these are discontinuous dynamic recrystallization or DDRX, continuous dynamic recrystallization or CDRX, and geometric dynamic recrystallization or GDRX. Okay, and we have also understood the dislocation mechanisms for each of these phenomenon as to how the dislocations play a role in each of these forms of dynamic recrystallization, right? In DDRX, you need a high strain build up in the material, and therefore the dislocation density has to build up. Okay, you need a high dislocation density inside the material in a particular region for it to go through the discontinuous dynamic recrystallization. Okay, so here you can see some transmission electron micrographs. So these are captured on aluminium based samples after deforming them severely. Okay, so you can see some dislocation structures here. Okay, and in this particular micrograph that you see in the first one, you see a lot of dislocations have built up inside this particular grain. Okay, so the dislocation density here is quite high in this grain. So if you compare any two regions, any two grains, for example this one and this one, there is a high gradient in the strain energy because the dislocation density is very different between these two grains. Okay, so this is what is needed for DDRX to occur. Okay, you need a strain energy gradient in the grains for them to go through the DDRX by that classical nucleation and growth mechanism what you have in static recrystallization. Okay, so if you have built up this kind of dislocation structures inside the grains, then you can expect DDRX to occur. On the other hand, if you have a material where the cross slip is prevalent, that means you have a material with a high stacking fault energy, then you may not have this kind of free dislocation build up inside the grains, because now the dislocations can cross slip and they will try and arrange themselves into some kind of low energy configurations. For example, if you see this grain over here, here you can see the dislocation build up is not that great compared to this particular grain. So here this grain is relatively dislocation free because dislocations would have moved by cross slip and other high temperature mechanisms. Okay. Now look at this particular micrograph over here. Okay, I'll show a blown up image also if I have somewhere. Look at this boundary over here. Let me try and magnify this right now here itself. Yeah, now probably you can see as to what has happened inside this grain. Okay, so here you can see a boundary. So this is basically a subgrain boundary which has formed due to arrangement of dislocations. Okay, and in fact you can see that dislocations are still coming and joining this subgrain boundary. For example, this dislocations, this one, this dislocation line over here. On the other side also you will see this dislocation line is coming towards this boundary to join it, and as more and more dislocations are absorbed into this boundary, the misorientation across this will increase. Okay, so this is a phenomena known as CDRX. So this is a continuous process of evolution of the boundaries, ultimately leading to grain refinement, right? Because if this boundary grows into a high angle grain boundary, then this grain will be fragmented in these two parts, right, across this boundary. So if you have more such boundaries forming in a grain, you can expect the grain to be divided into more number of fragments. Okay, so it is as simple as that. For example, you can see over here, this was a big grain in the beginning, the white color grain that you see. Okay, but now you can see there is a boundary over here, which is this dislocation boundary which has formed, then a boundary over here also, and then on the other side. Okay, and now you can see a clear-cut contrast between this region, which is bounded by these dislocation boundaries, and the original grain. Okay, so what it means is the misorientation across these dislocation boundaries has now increased, and that is why you actually see this contrast. On the other hand, if you see here, this is in the beginning, this is just evolving into a low angle grain boundary. So here the misorientation is not large enough to create a high angle boundary between these two regions. Okay, and that is why you do not see any contrast between this region and the region right of this particular grain. Okay, so it is still evolving, and the misorientation is still not large enough to divide the grain. On the other hand, here you can see a clear-cut contrast has already developed. That means the boundary that you see over here has already developed into a high angle boundary by dislocation rearrangement and further absorption of dislocation into such subgrain boundaries formed by the dislocation rearrangement. Okay, so this is a continuous process, as I said before. So this is the process of CDRX that you can see from these two micrographs over here. Okay, and as I said before, this will depend on the material property, particularly the stacking fault energy. So if you have a material like aluminium, the stacking fault energy is quite high. So if you look at the stacking fault energy of aluminium, it is in the range of 200 millijoules per meter square. Okay, so a value of the stacking fault energy in this range is actually quite high, and that is why cross slip will be prevalent in a material like aluminium. Okay, and therefore the dislocations will be able to move during this deformation process and they will arrange themselves into such boundaries, leading to formation of these small grains inside a big grain, which will ultimately break this grain into more than one grain and lead to grain refinement. Okay, but there is little more to understand over here. You will have to understand the character of these boundaries, and there is a very effective tool to highlight that. Apart from transmission electron microscopy, here also you can see the dislocations and how they are being arranged and what kind of structure is created by the dislocations. Transmission electron microscope also is a very powerful tool to highlight all this, but there is one more tool which can actually corroborate all these things and confirm that yes, this is what would have happened during the severe plastic deformation with regard to the dislocation structures. So let me take you through some EBSD analysis, as we call it, electron backscatter diffraction, which can be done inside a scanning electron microscope if you have those EBSD detectors. So it can actually analyze the character of the grains and the grain boundaries, and will tell you what is the nature of a particular boundary. Okay, whether it is a high angle boundary, it's a low angle boundary, or it is still in the subgrain boundary form. Okay, so here again I have chosen an aluminium based material, an aluminium zinc alloy, which was subjected to friction stir processing. Okay, so the severe plastic deformation that we are talking about here is FSP. Okay, so here again you can see the same thing what we discussed. Aluminium is a high stacking fault energy material, so you can expect the dislocations to arrange in this kind of low energy subgrain boundary configuration. Okay, so here again you can see a big grain, the white color grain. Okay, and in that grain, right at the middle, you can see this subgrain boundary forming due to dislocation arrangement. Okay, so now when this subgrain boundary turns into a high angle boundary, then this grain will be divided into two parts and the grain size will reduce. Okay, so that is how the dynamic recrystallization process leads to grain refinement in this particular case. Okay, it could be CDRX, DDRX, doesn't matter, but in either way, the bigger grain will be divided into multiple smaller grains, leading to reduction in the grain size. Same thing you can see here. This is just one boundary dividing the grains into two parts, but one grain can be divided into several parts, as you could see from here. Okay, so here you can see number of these dislocation boundaries are formed, dividing this big grain into three smaller grains. Okay, so the moment these subgrain boundaries or these low angle boundaries formed by dislocation rearrangement turn into high angle boundaries, this grain will be divided into three smaller grains. So that is how the grain size will be refined. Same thing once more, you can see clearly here they are still evolving. The mesh orientation across these grains are still not large enough to divide this grain, but now along a particular boundary, along this particular boundary, you can see the contrast has developed between this part and the other parts of the grain. So this boundary is already turning into a high angle grain boundary and creating a small grain inside this bigger grain. Okay, same thing would happen to these two parts also whenever these boundaries turn into high angle boundaries. And how this transformation from low angle to high angle boundaries occurs, that also we have discussed before. If you recall, more and more dislocations are generated during the deformation process, so more and more dislocation will come and join these boundaries, leading to an increase in the misorientation. And then we also talked about a lattice rotation, right? If you remember, that lattice rotation, which can occur during the deformation process, will also lead to a significant increase in the misorientation across such boundaries, leading to fragmentation of this big grain into several smaller grains. And as a result of that, the grain size will be refined. So this is a direct evidence, what is happening inside the material during the severe plastic deformation process, and how the dislocations play a role can also be observed directly through such tools such as transmission electron microscope. Okay, but in order to corroborate this, you also have to go into little more depth and understand the character of each of these boundaries, just to confirm that whatever we have understood from these images, that is actually true. Okay, so EBSD can do that if you do a thorough analysis and analyze the data carefully, analyze the EBSD data, then you can actually analyze the character of each of these boundaries. And that is what I'm going to show you right now. This is an EBSD image captured in an ACM having the EBSD detector. So here you can clearly see the grains and the grain boundaries. So what we do here, we take the base image and then superimpose the grain boundaries on that. Okay, so that base image is known as the image quality map, and we superimpose the grain boundary map over that. And if you do so, this is what you get. Okay, so the gray areas that you see, that is the original image quality map, the original image of a particular area of the material, of the deformed material, and over that, as I said, we have superimposed the grain boundaries. Now we are looking at each of these boundaries carefully as to what is their character in terms of the misorientation. Okay, so that can be seen with the help of the different colors which are given to each of these boundaries. Red color indicates a subgrain boundary with a maximum misorientation of 5 degree. Blue angle boundaries are the boundaries having misorientation from 5 degree to 15 degree, and anything above 15 degree is known as a high angle grain boundary, which is given a blue color. Okay, so you can see over here you have all these three boundaries present in this particular image over here. Okay, you can see the blue boundaries clearly. That means these are the grains which have already formed, the fine recrystallized grains bounded by high angle grain boundaries. So this also tells you that this is a well recrystallized equiaxed grained microstructure. Okay, you can see the equiaxed grains, and you can also see that these grains are also fine. Their size is smaller. Okay, so it's a fine grained recrystallized microstructure that you see over here. And now if you look at these individual grains carefully, you would see apart from these individual colors, that is red, green and blue, you also have a mix-up of colors. For example, here you can see a mix-up of green and blue colors. So what it tells you is that this boundary was in the beginning a low angle boundary which would have formed by dislocation rearrangement, and now it is in the process of evolving into a high angle grain boundary, and that is why it is turning into this blue color that you see over here, right? So this tells you that this process is happening continuously. The microstructure is evolving continuously. So this indicates towards occurrence of the CDRX process rather than DDRX. Okay, and the boundaries which would have formed by dislocation arrangement, if you remember, that is the dynamic recovery process. Okay, so rearrangement of dislocations into low energy subgrain boundary configuration is known as recovery. And since we are talking about the dynamic recrystallization process here, it is the dynamic recovery which is leading to arrangement of the dislocations into these low angle subgrain boundary configurations. Okay, you can also see a boundary over here, the white arrows, this one and this one. It is a mix up between red and green. Like here you have a mix of green and blue. Here it's a mix of red and green. So what it tells is, in the beginning the grain boundaries would have formed, that is the dislocation boundaries, and as the misorientation is increased due to absorption of more and more dislocations into the subgrain boundaries, it is now slowly turning into a low angle grain boundary, and that is why in the same boundary you see this green color coming. Okay, so this again tells you that all these boundaries are in the process of continuously evolving, starting from a subgrain boundary which would have formed by dislocation rearrangement to a high angle boundary which would ultimately divide the grains into number of grains, leading to grain refinement. Okay, now to prove this, we'll do little more analysis of this data, this EBSD data that we have. So we have collected data in terms of the misorientation, the grain boundary character, the strain which may be there inside a grain, or the strain across a grain boundary between any two grains, what is the level of strain. All that analysis can be done through this particular technique, and that is the beauty of this EBSD technique, that all this analysis can be done, and that will give you a lot of information about the material as to what would have happened to the material during the deformation process. Okay, so let us have a closer look again into these boundaries to reconfirm that what we see over here in terms of these boundaries is actually true. Okay, so this gradual transformation of boundaries from subgrain boundary to high angle boundaries, that is what we are proposing over here. So let us see whether that is true or not. So what we'll do, we'll simply take some measurement across any boundary, okay, any color, doesn't matter, and see how the misorientation varies across that line. Okay, so that is what we'll do. This is a blown up image. You can clearly see now all these different color boundaries and also the mixed boundaries. So what we'll do, we'll take a line like this. Let's say we choose this particular boundary over here, and we take a line like this. See the yellow line over here, and across this line we measure the misorientation. Okay, so remember these boundaries, the color code for each of these boundaries. Okay, green means it is 5 to 15 degree. It's a low angle boundary. And now if you see here, we have taken this line across a green color boundary, and you can see it is 14 degree. So this confirms that this is a portion of the boundary which is having a misorientation of 14 degree, or in other words, this is a low angle boundary. But in the same boundary you have another portion which is not green in color, it is rather blue. Okay, so let us see across that what is the misorientation, and we see that it is more than 15 degree. So it has turned from low angle boundary to high angle boundary, from green within 15 degree to blue more than 15 degree. And since it is a mixed boundary, you can see it is not significantly higher than 15 degree. It is 16 degree. That means it indicates that it is evolving from low angle grain boundary to a high angle grain boundary. Now let us see the other boundaries, the other colors. Here one more, that is again a mix. So you still have little bit of green over here, and that is why it is still within the range of low angle boundary. Okay, less than 15, but very close to 15 because the blue has already come into it. So it is already almost turning into a high angle grain boundary. Let's see the other colors. Yeah, the red one, you can see it is only 4 degrees. So this indicates that this is a subgrain boundary which would have formed by dislocation arrangement. One more, this is a mixed region. It is a mix of green and red, that is low angle and subgrain. So you can see this is little more than this portion where there is no mix at all. So it has increased from 4 to 5. So that means it is turning towards low angle boundaries, because here you can see the green color has already come. So this again confirms you this close analysis that we have done with the EBSD data confirms that the grain boundaries are actually evolving, and it is not like the nucleus has formed and then it is growing. Okay, so it is not the DDRX process involving nucleation and growth. Rather, this is a continuously evolving process. So it indicates towards the occurrence of CDRX. Okay. We can do little more analysis onto that to show actually what has happened to the dislocations. I mean, this will again reaffirm whatever we have discussed, whether these are actually dislocations or not. The subgrain boundaries that we talked about, if you do an analysis through something known as CAM map, it will show you where the dislocations went. Where did the dislocations go? Whether they are in the grains or into the boundaries, they have arranged into boundaries and all that. This particular map or this particular kind of analysis will show you that. So if you now superimpose the dislocation map over the grain boundary map, you would see that this dislocation map that you have in terms of this green color, you will see once you superimpose the grain boundaries on this map, you will see the dislocations are overlapping with the subgrain boundaries, the red color subgrain boundaries. Okay, so this reaffirms that the red color subgrain boundaries that we had seen before, these are actually dislocation boundaries, and then ultimately they are turning into high angle boundaries through a gradual increase in the misorientation across them. Okay, so this is how you can see the utility of the EBSD technique and the beauty of it as to how it can throw light on the character of each of the individual grain boundaries and help us understand how the microstructure would have evolved during the deformation process. Okay, so from here we understand that in this particular aluminium alloy, it was the CDRX process which led to the grain refinement due to the severe plastic deformation in the form of FSP that was given to the material. Okay. So with that we come to the end of this lecture, but I will see you soon. Keep watching.